In this video, we are going to continue our quest to become a master of the raster. And in this step, we are going to further delve into the overlay functionality or the overlay analysis capability in the Spatial Analyst Toolbox in ArcGIS. So to review, we've done a lot with DEMs, and we use DEMs as an introduction to the raster. And you should now be very familiar with the format of the raster. And we spent a lot of time in Raster Calculator, where we did simple queries of grids and, for example, queried the continuous surface for elevations greater than 250. And if it met that criteria, it became a 1, and otherwise it was a 0. And then we asked for slopes greater than, say, 45%. And if it was greater than 45%, it became a 1, otherwise a 0. So we created a bunch of binary grids and added them together using map algebra and Raster Calculator, and came up with a really very basic binary suitability analysis where if it was a 3, it met all criteria, 2s, 2 and 1s, and then we built on that and explored that. And now you should feel very comfortable with using Raster Calculator and performing binary overlays. However, Raster gives us much more a sophisticated ability to do overlay analysis, and we are going to explore the overlay toolbox using weighted sum, weighted overlay, and eventually fuzzy overlay tools. So that's the purpose of this video. And the best way to do this is by explanation and working with data. So to that end, we are going to jump into ArcGIS and explore the data that I've given you for performing these analyses. So what I've given you is a Malibu DEM, which you should be familiar with because we've worked with this now for 2 weeks in a row. And it's the DEM for the Malibu area. And I've given you a boundary of Malibu, a shapefile that's a boundary of Malibu. And I'm going to right-click on my Malibu DEM because it's always good to do data exploration. And I'm going to confirm that it is projected. It is in WGS 84, UTM Zone 11 North, and it has a cell size of essentially 10 by 10 meter resolution or 9.5 by 9.5 meter resolution. And I've also given you a soils and a vegetation shapefile. So these are vector shapefiles. And always, again, good to do data exploration. If I right-click on the soils and open its attribute table, soils is a very valuable environmental data set, and this data set I could spend more time explaining how we got it. In the lab document I have a source information, in the lecture I'll talk more about it, but it has lots and lots and lots of attributes, and one of the attributes here is the drainage class, and the drainage class gives you an indication of how well drained or poorly drained the soils are. So in our analysis I'll talk about how we've used that drainage class to create the data for the analysis, the weighted overlay. And then same with the vegetation. It's an attribute, opening up its attribute table. It comes from the Forest Service and it has a lot of different values in here. And the one that we're using in this analysis is cover type. And the cover type tells us what kind of vegetation it is. So I'm going to pause and go into the Word document and talk a little bit more about these data sets and how we're going to use weighted overlay to perform a suitability analysis. So the premise here for this assignment is that we're going to do a fire hazard analysis. And for fire hazard, here I have a review of the data sets that I've given you. We are assuming that fire hazard in this simple analysis is a function of slope, vegetation, and soils. So what we're going to need to do is, first of all, we understand slope. We're going to come up with some criteria for what we think is a hazard, a slope hazard. And for this data set, and this is something that I want you to change on your own when you're done with this lab, but when we're done with the demo, that is. So for slope, we're assuming that these are the classes. We have to reclassify the slope. So we're taking the old values of anything that's 0 to 1, so anything that's a low slope that's less than 1 is going to be a 0. Anything that's 1 to 25%, I'm assuming has a mild hazard. And assuming that there's this linear range where slopes that increase in percent have a severe and most severe fire hazard risk. So what we need to do in suitability analysis is reclassify our grids. So we have to reclassify old values to new values to create rankings. And then we're going to use these rankings, these ranked grids in our overlay analyses. So And instead of just zeros and ones, we're ranking them. And in our example, I'm going to have all of our inputs ranked in a range of 1 to 5. So when you do weighted and weighted sum, weighted overlay, when you do suitability analysis, all of your inputs have to have the same range of rankings. They can be all 1 to 4, all 1 to 10. But in this case, all of them are going to be reclassed into weights of 1 to 5, and then we're going to use those ranked grids in our suitability analysis. So I am going to rank our slopes, our continuous grid, into a ranking of 1 to 5. For vegetation, I'm also going to rank it into a range of 1 to 5. And I've done this in the vector. So I've added a field to the attribute table called veg rank, and it's based on cover type. So my assumption is that here are the different cover types, that if it's agriculture, it's mildly likely to burn. If it's barren, not so much likely to burn. If it's conifer or hardwood, it's most likely to burn. Maybe herbaceous is somewhat likely to burn. Mixed conifer is a 3. So I've taken my vegetation classes and I've assigned them a value in a range of 1 to 5, just based on my own assumption about how likely they are to burn. Now you can change this yourself afterwards. You can go into the vector GIS and do a number of select by attributes and recalculate the values. Similarly with the soils, I've assumed that if the soil is well drained, meaning it's very dry, it's more likely to burn. But if it's poorly drained, it's not so likely to burn. It's going to be wetter. So I've reclassified the soil vector based on that classification. So let's go back into ArcGIS and revisit this. So in my vegetation, if I open my attribute table, I have the cover type. And for example, if I go to select by attribute and I go down to find cover type, wherever it is. There's a lot of data in here. Cover type. Cover type is equal to get unique values. For example, I select barren and I select apply. It selects anything that's a cover type that's barren. And in this veg rank, I've assigned barren equal to a 1. So if I wanted to see what those were, I would just go to, if you want to change these, you go to veg rank and you would do field calculator and you could calculate them into a different value. But that's how I processed this data set before giving it to you. I assigned those ranks based on the cover type into the veg rank column. So those are all ranked 1 to 5 based on that table that I gave you in the lab. Similarly, the soils, if I open the attribute table, is also got a new attribute field called soil rank that's based on the drainage classification, based on the table in the lab. So I've pre-processed these data sets for you. And these are the values that we are going to use when we convert the polygon to a grid. Because remember, when you convert a polygon, which we did 2 labs ago, we did it with land use. We calculated the land use for Orange County based on the residential land use code. Here we're going to convert this vector to a raster based on this soil rank or veg rank attribute field. It has to have an integer value to grid on when you convert the polygon to a raster. So our first step when we do a weighted overlay analysis is to convert all our grids into ranked rasters. And so that's the first step. So what we're going to do is go into our student folder, and the first thing we're going to do is create a toolbox. And we're going to do this in a toolbox. So we're going to create a toolbox, and I'm going to call the toolbox overlay. And in the toolbox, I'm going to make a new model. And in this model, I'm going to go to Model Properties. And I'm going to set, of course, my important environments, my raster analysis, my processing extent, and my workspace. So let's set those values. I'm going to go to Workspace, and I'm going to set it to the Output folder. My current workspace, and I can just copy and paste that to get it out of the default geodatabase. My processing extent I want to set to the Malibu DEM. And my raster analysis settings, I want to set the cell size to be the same as the Malibu DEM, but I want to set the mask to my Malibu city boundary so that my output is clipped to the city boundary. So I've set those environments. I'm going to apply that. I'm going to go back to general. This is so important. You must check store relative path names. I'm going to change this model to, I forget what I tell you to call it, weighted. Let's call it weighted overlay. And we'll give the name the same thing as the label. And then you can give it a description, model for fire hazard, Geog 481, based on slope, soils, vegetation. You want to be as clear as possible in your description, so somebody who gets this model understands what the criteria were. You can add more information here later. Okay, so now we have our model ready to go. We're going to drag in our DEM, our soils, and our vegetation. And the first thing we're going to do is convert our vectors, our vector polygons to rasters. So we're going to bring in our tools from our toolbox, and we're going to go to Conversion Tools, to Raster, Polygon to Raster. So I'm going to double click this tool, and the first one I'll take is my soils, and this is so important. You want your value field to be that rank because we want a grid on that rank. Whoops, I want to grab the soil rank as my value field, and I'm just going to call it soil rank as my output. So now I've got my soil rank. I can drag that tool in again. Polygon to raster. The input this time is going to be veg, and here my input, the input is going to be veg rank, and I'm going to call this veg rank. All you have to do is give it the name, the root name here, and it puts it in your workspace. So you don't have to go searching for your folder and all that, and it's better to do that. Just give it that name and it automatically assigns it. See, so it knows where to put it. And then in order to get our slope rank, we have to do a couple of things. So we have to go into the Spatial Analyst toolbox, and we have to first calculate slope. So we want to go to Surface, Slope, and you should be much more familiar with these tools now that this is our third week with Raster. We're taking the Malibu DEM, and we'll call it SLP PCT for slope percent. And we want to make sure we tell it to calculate slope in percent. I must have one in there that's already called that, so I'm just going to give it a 2. That's why it had that exclamation point, or maybe I'll just do SLP underscore PCT. And apply and OK. So now we have my slope, but wait, it's not ranked yet. I have to do this reclassification that I alluded to. So that is in this whole set of tools called Reclassify. So you go to Reclass, this Reclass tool set here on the Spatial Analyst toolbox, and drag in the Reclassify toolbox. So the Reclassify toolbox is a little picky and finicky. So I'm going to select Reclassify, and my input raster is going to be my slope percent, and I'm going to reclassify on value. Now I'm going to go back to the table that I gave you in the lab and base my reclassification on these old values, new values. So I want 1, 2, 3, 4, 5, 6 classes. Now this is a note. We've already done slope. We've already calculated slope for this area. So I know that my slope range goes up to like 400%. But if you're working with a different DEM, you may want to do some data exploration, calculate slope outside the model so you know what your ranges are in your study area. So I'm going to click Add Entry 6 times. 1, 2, 3, 4, 5, 6. And I'm going to type in my old values and give it new values. So my old value is going to go from 0, and this is where it gets finicky. You have to put in a space dash space 1, otherwise it doesn't work. So my old value from 0 to 1 is going to be 0, and then I'm going to go from 1 space dash space 25. It's going to be a 1, and then I'm going to do 25 space dash space 50. The next one is 50 space dash 75, 75 space dash space 100, and I'm going to go up to the maximum of 100 space dash 400 because I think and this wouldn't work if I didn't have that space there. You have to be very careful. So it goes 0, 1, 2, 3, 4, and 5. Now this is going to reclassify my grid, and I'm going to call this slope rank, and apply, and OK. So now I've created all of my ranked grids. When I run this part of the model, if you wanted to, you could run this and just check, but make sure that you delete the intermediate data. So when we continue on with the overlay analyses, you don't have duplicate grids, but we'll have grids of 1 to 5, 1 to 5, and 1 to 5. So the next step is to add in our overlay operator, and the first one we're going to explore is weighted sum. So I'm going to drag that tool in here, and weighted sum is essentially a toolbox that could also be done in MapAlgebra. What it essentially does, if I double click here, I add in my rasters. So I'm going to add in my ranked rasters, soil rank, veg rank, and slope rank, and I'm going to assign them a weight. So what this is essentially doing is multiplying the entire grid by the ranking that I give. So I'm going to assume that slope has an influence of twice as much as everything else. Vegetation is more important and has an influence of 3 times of everything else. And soil rank I'm going to leave the same at 1. So essentially what this is doing is multiplying the grid by a factor of 3. So all of these range from 1 to 5. So veg rank is essentially being multiplied by a 3. So now it becomes a range of 3 to 15. And slope rank becomes a range of 2 to 10 because we're multiplying it by 2. And soil we're leaving at 1. You could give this a value of 50. You can multiply it by whatever you want the ranks to be, the weights to be. And when they're added together, the result, the maximum value would be 15 plus 10 plus 5. So 30. If there's any area that has the highest value you could possibly get is a 30 in this version of this weighted sum. So we are going to call this W sum and apply. And that's what weighted sum will do. And the next one we're going to explore is weighted overlay. Now weighted overlay is a little bit more complex. So I'm going to explain this one. So we already have our grids ranked, and it's also very tricky and finicky. But basically what you're doing with weighted overlay is you add in your grids and you set your evaluation scale. We already have our evaluation scale in 1 to 5 because we've already classified our grids as 1 to 5. So we must make sure that our evaluation scale is already set to that. And I'm going to now hit the plus sign and add in my raster. So the first input raster, I'll select soil rank, and then you have to do it again for each of your rasters. And the next one is going to be veg rank. And then my next one is going to be slope rank. Okay, so it automatically creates these values of, it's kind of a reclassification and a scale value. The scale value is what we want. So we have to go in and reprogram this. So you have to make it 1s to 5s for all of the classes and have them match. Just bear with me for this. So I'm going through 1, 2, 3, 4, 5, and I'm going to make this 1, and then you have to pull down to pull the value in. And this is because we ranked ours already. They're not continuous. So same thing here. The old value is 1, 2, 3, 4, 5, and it goes 1, 2, 3, 4, 5. Now slope, it doesn't really know what the values are, so it adds a lot more in here. Actually, it's working pretty well. So here 0 becomes 0 because we had a 0 in there. We'll make it restricted. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So now we've got our scales equal to 1 to 5, and what you do here is set the percent influence. So instead of giving it a 3s and a 2s and a 1s, you say what you think the weight might be for each of the input variables. So I'm going to assume that vegetation has a 35% influence. So I'm going to say 35, and these have to add to 100. And I'm going to say that soils have a 25% influence. And I'm going to say that slope has a 40% influence. And again, these are the things that you can change and alter and explore. And I'm going to call this I'll just call it W overlay. If I could type correctly. Okay, so now we are ready to run our model and go. So now we have a weighted overlay and a weighted sum and a beautiful model. We are going to save our model just in case. We are going to save our MXD just in case. I'm going to validate it and run it, and then we'll explore the output. Okay, so my model is done and the dialog box closed. But if you want to see the output, if you right click on the weighted sum and click add to display, it'll put the weighted sum in the display. And if you right click on weighted overlay, it'll put the weighted overlay and add that to the display. So we have two different weighted grids that are two different versions of our potential fire hazard in this area. And what I'd like you to do is think about what weighted sum does. And as I said, the maximum value is a 30 possibly here. It's a float grid. And weighted overlay ranks things in a range of 1s to 5s because it rescales it back to that ranking of 1 to 5. So 5 is the highest and 0 is the lowest. We may want to explore our properties, and we may want to go to symbology and switch the values. But anyway, you can explore the grids a little bit. This is our potential fire hazard in this area on a rank of 1 to 5 based on a weighted overlay and weighted sum. So it's two different ways of doing a suitability analysis. They give different results. It's similar inputs. It's the same inputs. It's just how you perceive what the ranking should be can change the output. How you apply the weights can change the output. So if you can imagine, there could be an infinite number of equiprobable or equally viable predictions of fire hazard in this area. And you can get more sophisticated and incorporate all of those, add them together, get a view of how, say you put 10 in the mix and then take the average of them. But for now, we have two different potential outputs of fire hazard that look quite different based on our input assumptions. And the rankings are the same, the application of the weights are different, and the method that we use to create the suitability analysis is different. One last thing, if you wanted to go into the properties here, because we have the count for the 4s and the 5s, we know how many grid cells are in these highest classes. You can calculate the area in the weighted overlay. The output for the weighted sum is actually, there's no attribute table available because it's a float grid. So if you wanted to get that attribute table, you'd have to go into Raster Calculator and convert it to an integer grid, and then you could figure out what are in the highest classes. But for now, I will leave it at that, and that is our weighted overlay and weighted sum. We'll do fuzzy overlay in a different video because it's a little bit different conceptually. What fuzzy overlay does is work with the continuous surfaces, and it works better with continuous surfaces. So we're going to use different input assumptions for computing fuzzy overlay for our fire hazard analysis. And that's our start. See you in the next video.